Okay, so we are going to look at classical machine learning algorithms this week. So we will start with a few of them. Um, so we are going to look at decision trees. We are going to look at um, random forests, and then how we can use gradient boosting with random forests, right? So you have XG boost. So gradient boosting is basically a gradient descent method that is kind of fine-tuned to be able to handle random forests and decision trees. Then we're going to look at support vector machines, k-nearest neighbors, and then we're going to look at clustering as well, using k-means clustering, dbScan, and dimensionality reduction. This is actually a lot. We won't be able to go into so much detail in all of this, but we will see how much we can do, right? So we start first of all by the classification we have just done, right? Sorry, the regression and you know, we've just done. We will yeah, we will do it with sklearn, right? But let's look at sklearn first. We had already looked at it. sklearn is scikit-learn or scikit-learn, right? It's a widely used open source machine learning library for Python, and is built on the other Python libraries, basic libraries, including the NumPy, which we have used NumPy extensively already, Skippy for scientific and technical computing, and Matplotlib. So scikit-learn contains a lot of stuff, right? A lot of this stuff that we have done manually, right? Scikit-learn will basically just give you a single function that says fit, and you do it. And we will try some of these same tasks that we have done using scikit-learn. The only thing is why I went through all of the trouble to take us through doing it manually and then doing it ourselves was so that you understand all that is going on under the hood. And it helps you to have a better and more nuanced, idea of what is going on. So scikit-learn has a comprehensive collection of algorithms, right? Um, for various different tasks. So even like this linear regression, logistic regression, classification, they're actually functions or libraries that handle that. So all of those things that we were doing manually, right? We don't need to do them manually anymore. It can do other stuff, right? Using other methods. For example, this support vector machines, right? The SVMs, the decision trees, the random forests, right? The k-nearest neighbors, and all of that. Okay. So the kind of things you can do linear regression with scikit-learn very easily. You have what we call ridge regression. You have what we call lasso regression and gradient boosting for predicting continuous numerical values. Then you also have clustering algorithms, like we've already mentioned the k-means clustering, dbScan, agglomerative clustering, for grouping similar data points. Then dimensionality reduction using principal component analysis, PCA, linear discriminant analysis, LDA, and all of that. So one of the other things you see that it has a consistent API. So like it is a standard API. So the way you do logistic regression, linear regression, the way you call the method or the function is the same as the way you call others, right? So because it gives us consistent API, it's easy for you to do anything because you don't need to try to remember, okay, how do I call this function? Or how do I call the other one? Or how do I do this one? Or how do I do the other one, right? It makes it really easy for you to remember and call. So if you want to do we are going to look at some examples just shortly, right? Before we close. But you know, you don't need to try to remember how the things, how to call stuff, right? The only thing is for you to just um follow that same pattern. Okay. So the other thing is it has data preprocessing and model selection tools, right? So um, it really has this thing they call pipeline, which we are going to look at. It helps you to basically connect your data processing straight to your model training. In fact, your model selection, of course, first of all, model selection is easy because it has the same API, right, for you to switch between different types of models or approaches for training. Oh, sorry, for solving these problems, right? And then it takes you all the way to the training thing. So it has a complete selection of tools, right? So you can use for data preprocessing things like scaling, normalization, and handling missing values, right? I saw some people actually use the scikit-learn's normalization API to normalize. So you can use that. Then for model selection, right? You can use it to split data into train and testing sets for cross-validation and hyperparameter tuning. Because these are some of the key things for model selection. When you have multiple models and you want to determine which one is the best fit for a particular problem, you can take a subsample of that data, right? A small subsample, and throw it into the model selection algorithm where you can try different models, so you have data splitting, you have the entire pipeline, data splitting, then you have cross-validation data set. Cross-validation allows you to compare the same data set, the same performance on the same data set across multiple different types of models or model architectures, right? Then you can tune hyperparameters, right? And you can even automate the tuning of hyperparameters using things like grid search and, others like that, random search and so on, right? So in that process, it will quickly pull out for you, oh, this is the performance of this model in this and the other model in that. Then you can do model evaluation as well. You can check metrics, you can assess models. We have accuracy, precision, recall, F1 score, which is a combination of the three. And then you have mean square error, root mean square error, R squared, and so many others. It's also very efficient. It's highly integrated, so you can use it NumPy. It delivers good performance, and it also integrates seamlessly with other Python data science libraries. So like pandas that we used for data manipulation and so on. It has a strong open source community. It has support. So you can always ask questions if you have challenges, and it will be easy to get support. So we are going to do a simple hands-on session, right? With using the same regression and classification. We'll just do the linear regression and logistic regression. Okay, so we're just going to do that. Do you have any questions? So let's start off. If there's no question, I'm going to kick off. Um, I'll start by I'll create a new, yes. So take note, what I want to do is basically the same problems we have just solved, right? With linear regression, with multiple variables. I am going to bring up those same, and I'm going to solve them with sklearn, right? Just to demonstrate to us how much simpler it is, right? It will be interesting, for me to do this because it will be like, oh, okay, if it is this much simpler, why are you stressing us? But I hope you know why I'm stressing you. Do you know why I'm stressing you? Right? I hope we agree. Okay, so So I have the data set. This is the data set that we've already used to solve a specific problem with um with this was linear regression. Okay, this was linear regression with single variable. Okay. So we will do this, then we'll do the linear regression with multiple variables, and then we'll do the logistic regression. Okay, so let's run. So while I'm waiting for this to run, yeah. So for even the other interesting thing you see with scikit-learn is they even give you data sets. Like you can actually just pull data sets here anywhere, right? But I'm not going to pull data sets. We'll do some other problems with their data sets. The more complex, when we want to use decision trees, random forest, right? Yeah, we'll do that. So I'm not going to do model selection, right? I'm just going to do, I'm just going to do, so we import a linear regression model. You see how simple it is? You import a linear regression model, right? From sklearn.linear model, import linear regression, okay? Right. Now, I'm not going to do train tests. I'm not going to do train tests. We'll come to that when we want to talk about how to fine tune this thing, our code. But I just want to do like, this is how simple it is. Model equals linear regression. Then you just fit and you reshape it, right? So we are reshaping X. X is expected to be a matrix that has dimensions. So first of all, you can see that if I were to print our X and Y here, X, Y, right? You see that, okay, let's do X shape, Y shape. We already know what X and Y looks like. So X shape and Y shape, okay. So 2020, but for, remember that vectorized thing I said, X has to have two dimensions. In this case, X has only one dimension, 20 and 20. So if I don't reshape this X, right, it's going to give me an error. All right, it's going to say expected 2D array got 1D array instead. That is the X, right? So reshape your data either using this. So typically the X that you pass in, the Y can be one dimensional because the Y is just expected, true values or labels. But the X has to be two dimensional. So even if it is a one dimensional, you need to explicitly mention the second dimension. So if you know NumPy very well, you have what we call reshape. Reshape is to say, okay, change this shape. The minus one means keep whatever is the first batch, but let the second, keep whatever is the first dimension, but let the second one be one. Okay, let the second one be one. So if I were to print this out, you know, x dot reshape, there are many other ways you can do reshape, but I guess this is the cleanest one. You can see, okay, I don't need the actual values, but I just need the shape. So when you reshape, you can see it now has two dimensions. The second dimension is explicitly mentioned that it has only one column, 20 rows, one column. Here is a vector. So we already a one-dimensional object. So we know that we don't need to worry about how many columns it has. We know it has one column. But that's because if you want to do a multi, right, you now see how much easier to do linear regression with multiple. Now, so this is all good. So we run it now. Um, so when you do this, okay, what happened was I created a model that fit will train the model. But when you train the model, you can then do stuff with the model. So the first thing you can do is model.predict, right? I can predict the entire Y, X or reshape, okay? That will now give me the values. So after training the model, I predict. Of course, it's the same thing. 3 lines of code. Simple. This is what we were doing loop. Okay. We did not even specify the number of epochs because sklearn can basically get some epochs, but it uses other things we call stopping conditions, which I didn't want to go into because it's a lot to do, right? A stopping condition is, okay, what makes me stop? Maybe we'll talk about that as well. So the fact that we're using sklearn doesn't mean that once in a while we'll not go back to linear regression and learn some of the basics, right? So this is it. Now we can then go ahead and print the stuff, right? We can plot all the stuff that we used to plot, right? We can plot a scatter of XY to see how good it is. We can also calculate the MSE, mean square error, right? So to calculate mean square error, sklearn also has, like we said, evaluation libraries. So the evaluation functions are in sklearn.metrics, right? So we can import the mean squared error, which is the MSE. So we can just, to do the mean square error, we will now, we already know the Y values, okay? We'll talk about test and train later on, but for now, I just want to tell you how much simpler it is. So I can predict, when I predict, I can now do mean square error of Y, and Y is the actual value, and the this is the model that predicts the Y that is predicted by the model. Okay, I need to rerun this because I just imported this. So you can see the mean square error is 2.79 and it has plotted the graph. So the thing that we were all struggling with, how many lines of code? Some people wrote a lot of stories. 3 lines of code with sklearn. So, well, the thing is that all of that code that you wrote by yourself, that's what is inside this linear regression function. So effectively, what you were doing is you learned how to write your own linear regression function. You know, if you wrote something like, if you wrote a function, some of the people that submitted these things, I think you wrote your own function that you called it, gradient descent, blah, blah, all of that. That's the same thing now. You just wrote the thing now. You just wrote it. So, and this is the same pattern for sklearn. Okay, now, let me make this smaller. Plot dot figure. So I'll make it a smaller figure. Don't worry. I know I told you enjoy it from this week, but I want you to suffer so that you know the value of sklearn. If I didn't make you suffer, you will not know. You will not value, and you will go and pray and thank God, thank the people that wrote sklearn. You will not play with them again. Okay, so yeah, so I scatter, I want to scatter with a red color. Okay, no, I want to predict with, I want to predict with red color. So dash dash. I hope this works. Yeah, okay. So yeah. So now this is linear regression. We can now do the same linear regression function. We'll now do the second problem, the Kaggle problem, right? The Kaggle data. So yeah, we'll do this. I'll copy this cell. Right. So we have the Kaggle hub. I don't even know if, okay, we need pandas to load the data. So we get Kaggle hub in. Then we load this, right? Oh, sorry. So I now import all the data, right? So yeah, so this is the data. This is a multiple linear regression, okay? So we will now extract the X. I'm not going to do any normalization for your information, right? I'll see what sklearn does with this, right? Because this particular problem, by the way, some people that did this problem, we are going to do some review. I'll make out maybe like 5, 10 minutes to review the stage, is it stage one? Yeah, stage one task. Um, a lot of people got high gradients. A lot of people didn't converge because when you were having these large gradients, you could not figure out how to tackle it, right? Some people use very low learning rates, but they did not increase the epochs to match, so they still did not converge, right? And some people basically just did not know what to do, so they got stuck at the high learning rate, high gradients, okay? So, but anyway, so to get our values, you can do values, right? Because values will give you numpy. So we can just get x from data. I'm not going to use iLook, right? I'm just going to use the column names. So the column names will be age, right? And experience. And I'll get the values from it. Then this is income actually, not salaries, but that's okay. Okay, so this is now XY for the second problem. Well, okay. Let's do XY first. I can also do the X shape as well. Let me do the X shape here. So I can do X dot shape. I do display. I use display to still display the same way. X dot shape. So we can look at the shape of X and the shape of Y. Okay. So if you run this now, so you see shape of X. This is two-dimensional, and shape of Y. So this, you don't need to reshape the X now because we pulled it properly from this thing. I assume this is a numpy array, but if it is not, then we'll turn it to a numpy array. So we still do the linear regression. So you can say linear. We can still use the same linear model, by the way, right? Because this linear model has no prior assumptions. You just give it a value to fit, and it fits. Okay. So, but let's start a new one because if not, so let's say model 2 is linear regression. We now fit that one. Still the same XY. We can now calculate the mean squared error. Let me see what I did here. Yes. You see, you get this 1533, which is the correct mean square error, right? This is actually the correct error if you did not normalize the Y value, if you did not normalize the output. Some people normalize both the input and the output. Normalizing the output is kind of problematic because when you normalize the output, when you want to predict, you have to remember the normalization factor and you have to denormalize the prediction from your model because your model is, if you normalize the output and use it to train your model is trained on a normalized Y value, right? So if you predict with that model, and some people did that, you get a value, but it's not correct because it's not mapping to the original Y values. So you have to denormalize it. And there are a bunch of people that did that. And kudos to, anybody that thought about that, right? But remember, when you're denormalizing, you use the same factor you use to normalize to denormalize, right? So, but if you don't normalize the Y value, you normalize only the X, you will actually get a fast convergence as well in 1,000 epochs with a learning rate of 0.001 or thereabouts, or 0.01. Some people even did 0.01, right? But if you use the unnormalized inputs in this particular problem, your gradients will blow up. And the reason is simple. Your gradient actually depends on X. Remember, gradient is equals to X times the what do you call it, residual. And the residual is a large value that comes from subtracting this thing, right? It's X dots, it's a dot product. So the residual is a large value that comes from the error between what you are predicting and what the actual value is. So if the values of x are reduced by 10, your gradient will be reduced by 10. So that's why it's very important. But your y value does not really affect your gradient. The y value comes into the residual. Remember, your residual is y pred or y hat, y pred minus y. That's your residual. So if your y is large, right, the y pred may also be large. So because that's a difference, right, the residual may not be as high as the y itself, but it will be high the first time. Let's say your y pred is 0 and your y is very high, right? So you have a high residual. But the x will make it even bigger. So your gradient will be really big. Now, because you are updating your gradient, remember you're updating each parameter by learning rate, right, times gradient. Dot mean, okay, well, whatever. This is pseudocode. I'm not really typing stuff here, right? So it is your learning rate that you use to bring down the impact of a large gradient. So if your gradient is large, your learning rate has to be low. But remember, if your learning rate is low, your fit would take longer because it's taking smaller steps. So because it's taking smaller steps, you need more steps to get to the optimum. So you need more epoch. So if your learning rate is low, like 0.0001, your epoch needs to be much larger. So these are the things you need to think about and know. So there is interplay between all of these things, right? So I just wanted to point this out. So I think in this case, the best approach was normalize the input, leave the output, right? And you still converge with a high learning rate of 0.01 and 1,000 epochs, right? I can prove that. But if you don't normalize anything, you will need a very low learning rate to avoid blowing up your gradients. So you have 0.0001. But because you have such a low learning rate, you need a large number of epochs, maybe 1,000,000 or 500,000 before you converge. Okay. Then, if you do normalize both input and output, you will still converge in the same time, almost the same time, right? Your error will be much smaller. Of course, it will be a very low value, like 0.0029 something. But you will now have to remember to denormalize when you are predicting. Now, I just wanted to see what sklearn did. Sklearn normalized the input, it didn't normalize the output. That's why we have this large error, but it has converged. Now, how do I know that it has converged? By plotting, I plot the x, I plot the y against y, right? So I don't need to plot the, I can do all of that, but let's just do a plot. Figure 4.2. Okay, let's make it to it's 4. Okay. All right. So I want to plot y against y pred. So y and y pred. Yeah, this is this. That's all I want to plot. So this will give me an idea. It's going to be circles. It's going to be red circles. Red circles. All right. Okay, it says scatter, so I don't even need to specify. I just need to specify the color, but red circles. Um, I'm trying to figure out where this is coming from. Why? Okay, let's see what we get from predict. So model 2 dot predict x. Just this alone. The shape. Okay, so it's 20, right? And y, the shape. Okay, so it's the same. So I'm missing something. Okay, the arrow shouldn't be here. Sorry. All right, so now I always like to also plot plot y, right? I plot y against itself as a way to just measure and say, okay, so the y against itself, I need to make the color red. So color equals red, red. Uh, color equals red. Okay. Um, okay, maybe put this in quotes. All right. So the blue line is the line of the correct prediction. The red line, the red dots are the predictions from our model. So you can see that our model is very close. There are a bunch of submissions where if you go and plot this line, so this is a plot, you can take a look at it. Plot y against itself, right? And then after that, do a scatter of y against your prediction with red color. You will see that you see that you know for some, if your model is not well trained, it's going to scatter all over the place. It's not going to match. This is really close to it. So again, you see how fast this is just a single line of code. Okay, single line of code with sklearn. That's why people love sklearn. It basically simplifies, especially all of these basic things that we do. Now the last one, we can do logistic regression. Okay. Should I do that? Because that question is still under, I won't do that. So, but anyway, I think we can still do it. I don't have logistic regression here. So this is just showing you how good sklearn is and how much stress it takes away from you. But it also allows you to understand, you know, contrasts when you're doing it yourself. But at least now that you've done it yourself, you feel fulfilled. So I'm going to stop there for today. Um, one, I'll stop the recording and we can have questions after.